Okay, let's do this improper integral, the integral from 0 to infinity of t times e to the negative 4t. With respect to, this should be t. So I'll just change that. So let's calculate this improper integral. It's improper because one of the bounds has an infinity symbol in it. So the first thing we're going to do is remind ourselves what this actually means. The integral from 0 to infinity of t e to the negative 4t dt, of course, is just what they actually mean is the limit as n goes to infinity of the definite integral from 0 to n. So I've replaced the infinity sign by n, and only at the end of the calculation do I let n go to infinity. T e to the negative 4t dt. So now what I'm left with is just doing this definite integration problem. This has nothing to do with improper integration anymore. I just do this definite integral here. And only at the end of the question do I let n go to infinity to actually calculate what the value of this improper integral was. So let's just focus on the definite integral here. So nothing happens with this limit. We're not worrying about it for now. Let's just look at this definite integration here. I can't think of any real antiderivatives off the top of my head, so I'm going to have to use some other types of methods, maybe substitution, maybe integration by parts. If I look closely at the form of this integrand, I notice that I would rather not have this t here. If I didn't have this t here, this would be very, very easy to do. So if I recall that the derivative of t with respect to t is just 1, if I could just take the derivative of this, it would go away. And that's actually something that integration by parts lets us do. It lets us convert something that looks like this into a different integral where I'm actually allowed to take the derivative of one of the pieces in the integrand. So integration by parts is probably a good idea for this question. So what we're going to do is integration by parts, and so I'm going to go over the first thing I have to do is choose which is my u and which is my dv by dx, or in this case dv by dt, and the u that we want to choose in this case is the thing that we want to take the derivative of to make our life easier. So I'm going to choose this to be u, and which means this part is going to be my dv by dt. So I'm going to go over here and figure out all the rest of the pieces for my integration by parts. I have that u is equal to t, which means the u by dt is just equal to 1. I don't know what v is yet, but I have chosen that dv by dt is equal to e to the negative 4t. So if this is dv by dt, this is the derivative of v with respect to t, I can easily calculate what v is just by doing the antiderivative of this, which is negative 1/4 e to the negative 4t. Okay, so I have my pieces now for my integration by parts formula. So this actually ends up becoming the limit as n goes to infinity. We haven't really dealt with that yet. And what I'm going to do now is use my integration by parts. So this is going to be u times v, so t times v, which is negative 1/4 e to the negative 4t. And I'm going to evaluate that between my endpoints, 0 to n. And then the second piece of the integration by parts formula, I still go from 0 to n. But I now have to calculate a different integral, not the original integral that I had, but a different integral, namely v times du by dt. So v is negative 1/4 e to the negative 4t, and du by dt is just 1, so I have a 1 here, and then I integrate with respect to t. Okay, so let me just get a little bit more space. This is the limit as n goes to infinity. I'm just going to clean up what this looks like inside here, but I'm not actually going to calculate anything. I'm just going to bring the negative 1/4 out in the front. So this is negative 1/4 e to the negative 4t. I'm going to evaluate between 0 and n. And then I'm going to realize that here I have this negative 1/4 multiplying these functions. This is just a constant as far as t is concerned, so I can pull this outside of the integral. This becomes plus 1/4, and then I'm still left with this definite integration between 0 and n e to the negative 4t dt. Of course the 1 goes away because 1 times this is just itself. And now I'm in a situation where the last part of the definite integration involves just calculating what this definite integral is. And this is actually something that is very easy to calculate because I know the antiderivative of e to the negative 4t. So I'm going to leave everything else alone. I'm not going to do anything with it at this stage. T e to the negative 4t. Still going to evaluate between 0 and n, plus, now let's do the plus 1/4, that's still there, and let's do the antiderivative of this. So the antiderivative of e to the negative 4t is negative 1/4 e to the negative 4t, and I'm going to evaluate this eventually at the endpoints 0 and n. Okay, so let's actually see if we can go ahead and start plugging in our endpoints now. We still have this limit as n goes to infinity of all of this, but let's plug in our endpoints. We plug in an n, and we get negative 1/4 n e to the negative 4n minus what we get when we plug in 0, which is negative 1/4 0 times e to the negative 4 times 0. Okay, so that's the first part. Then I have plus 1/4, and let's finish this definite integral by plugging in our endpoints. Negative 1/4 e to the negative 4n minus what I get when I plug in 0, which is negative 1/4 e to the negative 4 times 0. Okay, and I can obviously simplify a lot of this. This becomes limit as n goes to infinity. Haven't done anything with that. Here we have negative 1/4 times 0 times e to the power of 0. So this is just 1. But everything in the second term is multiplied by 0. So that wipes out this whole term. This whole second term goes away. And all that we're left with in the first part is negative 1/4 n e to the negative 4n. That's all we're left with from this first piece here. The second piece, we still have this plus 1/4. And what we can do is we realize that e to the power of 0, because negative 4 times 0 is 0, e to the power of 0 is 1, so this becomes negative 1/4, but I'm subtracting it, so it's minus negative 1/4, so that just becomes positive 1/4, so I'm just going to pull that out in the front. And then I still have left here negative 1/4 e to the negative 4n. Okay, now I'm actually in a position where I might want to take the, well, I can actually, how about I expand, just for simplicity, I'm going to expand or distribute that 1/4 in. So the first couple terms stay the same, e to the negative 4n. I'm just going to multiply this 1/4 in. I have plus 1/16, because 1/4 times 1/4 is 1/16. And then 1/4 times this is negative 1/16. 1/4 times negative 1/4 is negative 1/16, e to the negative 4n. And so let's now figure out what happens when I take n to infinity. Okay, as n goes to infinity, here I have something that is a number times n to the power of 1, e to the negative 4n. And this is of the form where we know that this actually goes to 0 as n gets really, really big. Even though this n out front is actually getting very big, a million, a trillion. The exponential, when n is getting really, really big, this is a really, really large negative number. And so the exponential is getting very, very small. This second piece is actually getting very, very small. And this piece will actually get smaller much, much faster than this first piece. So even though this n is getting very large, the exponential is getting very, very small. And at the end of the day, this exponential always wins the battle. And so this will go to 0 and wipe out everything else in its path. So this goes to 0. And of course, over here, we don't even have any competing. We don't have an n in the front. So e to the negative 4n, as n gets really, really large, this also just goes to 0 and wipes out everything. So this goes to 0. And all we're left at after taking this limit is 1/16. So this improper integral is convergent, and the answer is 1/16.